That's a nice tool to have in our toolkit. Now we're going to do the same thing, but more in the style of the roller coaster. So the issue right now is we just had one parameter, the angle. And we knew the pendulum would just move around with the same radius all the time. But the physics works out just the same way, or better, if we treat the pendulum as a thing just hanging in x and y. So we say, to heck with all that complicated torque stuff. Let's just pretend we have a mass at the end of a rod of length L, and we have two forces on it, F of gravity and F from the rod. And we're just going to keep it with, I guess we could have friction here. F friction, which would be perpendicular to that. We're going to forget about friction for now. It's easy enough to add back in later. There's going to be enough complexity with the rod and the gravity. But if you believe in Newton, and we all believe in Newton, then, or at least his ideas, he's a bit of a nut bar in some things, but anyway. So the gravity and the friction are the only two, gravity, friction, and the force of the rod are the only things acting on this mass at the end, right? Some of these forces are super easy, right? F of gravity is just 0 in the x component, so we're going to do our x and y components here, x and y, and negative mg is going to be our force of gravity, x and y components, x, y components. So if I wanted to model this as mass times acceleration, I'm going to model it as a vector mass and vector acceleration. Sorry, not really vector mass, vector acceleration. We can model the forces as vectors as well. So this is, again, pretty vanilla first-year physics. The only complicated part comes in when we get to the rod part. What we're going to do is define our axes to make life a little bit easier on ourselves. We're going to define our axes to be centered at the pendulum center of rotation. And so if we're at the coordinates x, y here, and the rod force is going back up this way, call it FR, what direction is that pointing in? Can someone give me a vector that would point in? 1, 1? I would agree if that was actually where I drew it. But what if I drew it over here instead? Made your life miserable. So x and y can also be here because we're rotating, right? Or it could be down here. So it's not always going to be 1, 1. If I know I'm at the coordinates x, y, and this point here is 0, 0, which direction is this arrow pointing in? Is it negative x, y? Right. If you want a vector going towards 0, 0, you take the 0, 0 minus the x, y, and that gives you negative x, negative y. Take the end minus the start. So negative x, negative y. And there's going to be some magnitude to this, so there's something that's still missing. But we know the direction is going to be towards the center. It has no choice about that because the rod can only exert longitudinal forces here. Now the magnitude is where it gets fun. So the magnitude is going to be derived from a whole bunch of different properties here. And this, let's talk about gravity here, Fg. And we have the rod force coming up this way, F rod. And what we can do is, of course, talk about components, right? We're going to talk about perpendicular components like so. So we're going to have some issue with components. Let's call this part here, this vector here, the F gravity with the rod component. Parallel to the rod component is actually what it really is. That's this vector here. Now, how do you think those two forces have to be related? I didn't draw them to scale. I didn't know what the scale was going to be yet. So how do I think those two forces should be related to each other? They should be equal. That is so tempting, and that's honestly what I thought for about 2 days when I first developed this lesson. That's wrong, though, because let's figure out why. If they're equal, then what happens is all the acceleration is this way, right? Because if the net component parallel to the rod all cancels out, then our acceleration is purely perpendicular to that. What do I want to have happen, though? I want to have this thing go in a circle, because it's a pendulum and it should turn up. If my acceleration is all this way, though, guess which way I'm going? Plow. I'm not going to follow this circle at all. And if you think for a second, wait. It's radial motion, it's circular motion. The acceleration towards the center for centripetal motion has to be what? mv squared over r, right? So there actually has to be a net centripetal acceleration has to be mv squared over, well, we have a length of a rod L. So this is a surprise, honestly. I mean, you look at this diagram and you think of all the plane things that you run down. You think these things should cancel. But actually, to have this work, the rod has to pull a little bit extra so it doesn't go straight, so that it does pull up and end up in circular motion. So the F rod is actually a bit bigger. The nice thing is it turns out it's easy to work with that, because the magnitude of that force is equal to the magnitude of the rod force plus the magnitude of, as a vector, plus the magnitude of the F gravity rod component. Because we're just talking magnitudes here, we know the direction, we're just talking magnitudes. So whatever the rod and the gravity force fight out, I guess actually it should, if they're absolute values, this should be negative, minus. I know the acceleration we have to have in the end, and I know the two forces that are being applied, so I have to add those up and make it work. And fortunately, we know this guy, or we can figure that one out. So what we're going to do is just solve for what we need to know, which is, hey, the one unknown in this picture is how strong a force does the rod have to exert? Well, it's going to be based on the current velocity, and it's going to be based on the component of gravity that's actually parallel to the rod. It's just combining a bunch of first-year physics together. Does that make sense? We're going to solve for the rod force here. This kind of derivation is very similar for those in the roller coaster. You're going to do the same thing with the curvature of a track is going to have the same element of the curve of the track has to be followed, so you have to have a net centripetal acceleration there as well, just to give you a flavor. So now we need a formula to figure out what the actual F rod is as a vector. So what we're going to need here is the magnitude of the rod force is equal to mv squared over L plus, and this makes sense in a second, rod component. If there was just the rod and there was no gravity, it would have to pull inwards. But because gravity is also pulling outwards, we have to cancel that, so we need a bigger force than just gravity. We need to have gravity plus the net centripetal acceleration. What we're going to need here is m. What we have in our picture is a position x, y, and we also are going to know the velocity. So we're also going to have x prime, y prime. We're going to have those two velocities. So the velocity squared is going to be the square root of x prime plus y prime each squared. That's our speed. Actually, that's a good point. V here is not a velocity in this formula. It's always been speed. Unfortunate notation, but there it is. We're going to have that all squared and over L. So we're going to have our x velocity or y velocity, each squared, square rooted. The whole thing is squared because it's v squared. And that gives us the centripetal acceleration factor in terms of where we are and how fast we're going right this second. The gravity component is not too awful either. Fg, rod. Fg is going down like this. Sorry, let me draw it so it works. Right angle here. And now we're getting into some vector stuff. So Fg is here. We have Fg as a vector. If I want to project it down onto the rod direction, what's our favorite friend if we have vectors we want to project? What do we do? Dot products, exactly. So we just need a vector in that direction. Well, we actually just said the vector xy would do nicely if we want to point this way, or if we want to point the other direction, that would be negative x, negative y. That's the direction the rod is pointing in, because it always points back to the center or outwards along the same axis. So we can do a nice thing here, which is, let's find out, we want the magnitude. So we're going to project it, let's project it on the positive sense. So xy is a vector that points in that direction. And gravity is going to be down like this, so we can project one onto the other. So we're going to take Fg dotted with the xy as a vector. And that'll get us a projection onto the rod direction. Okay. Now there's a little, x and y isn't quite good enough. If x and y were really, really big, I'd get a really, really big dot product. We have to do something first that you often do with these kinds of projections. Normalize unit vector, exactly. So we're going to, actually, let's do this. Let's call this new vector u, and we'll call this u is going to be the xy vector divided by its own length. so it's a unit vector, or normalized. Okay, so that's our magnitude, and we're going to have to get some fishy stuff going, but I think it'll make more sense when we put it into the code. So last piece, we're almost done. This is the magnitude. We actually need to get a final force. We're not going down here. We need to get the rod as a vector. So F rod as a vector. Let's call this whole thing here M, magnitude. We can calculate that out. And let's just do a quick little calculation here. That's going to be positive. These are both scalars. So M is a scalar. This is important to distinguish. We've got a scalar here. So it's going to be that M. Oh, M's a bad word, isn't it? It's also our mass. Let's call it big R. Big R for the rod force. Times the direction. And again, we're going to need another unit vector here. So I'm going to try this with U. We're going to try that. Sorry, not dotted with U. This is R times U. Because we have the magnitude and the direction with a unit vector. I'm just going to do a quick little mental check through this, because signs are an issue, or plus and minus things are an issue. FG dotted with U. So U is the vector going this way. We expect FG dotted with that to be positive, because they're both pointing in roughly the same direction, at least in this picture. So we're going to get a positive, that works. And then, Gesundheit. The only problem here is this vector would point, I think it would point downwards, because U is pointing downwards. I think we're going to need to put a negative sign in here, because the direction the rod force is in the opposite direction of U, so it'll actually need to be negative U. This is the kind of thing that we can work it through on paper, but if you're never quite sure, we'll see if the math in the simulation works this way the right way.